All right, so hopefully most of you have gotten the textbook by now and also have your calculator. We're going to start working with the calculator next week, so make sure that you have your calculator all ready to go. As far as chapter 2 is concerned, I realized when I was doing a review of the updated 6th edition that they've changed chapter 2 a little bit. That's okay, Mattia, that's fine. It's all right. They changed chapter 2 where they haven't put very much into section 2.1 that they moved it into sections 2.3 and 2.4. So what I'm going to do today, actually, I'm going to change the syllabus a little bit. Today I'm going to cover sections 2.1 and 2.2, and then next time 2.3 and 2.4. All right. So what was originally supposed to be 2 sections will now be 4, but it's basically the same information. It's just the authors decided to spread it out a little bit more than they did in the previous version of this textbook. All right, so let's look at 2.1. And I will post 2.1 later today, with this copy of this recording. All right. Okay, so this is, hopefully you can all see this. Joseph or Keon, if you could just give me a thumbs up if you could see it. Can you see the, yeah. I happen to see your, yeah, good. All right, thank you. So this section 2.1 is fairly short, and it basically deals with, in a very general way, the types of studies, research studies that statistics is used in. And there's some terminology in here that I would like for you to put some attention on. So let's go ahead and take a look. All right, now one of the big issues with statistics or a researcher is that what a researcher needs to do is needs to, of course, come up with a research question, very specific question that they're interested in. And then they need to determine the variables that they need. And then the next step would be basically, can they find the information from a data set that's already available? Or do they have to collect the data themselves and create a new data set? So this section basically, this chapter basically is assuming that you have to collect your own data. And, but obviously you don't have to, right? If you just, if the data set's out there. Now, that would be for what's called an observational study. If you're doing an experiment, obviously, an experiment would be original data, all right? You wouldn't be necessarily looking at somebody else's data. All right, so we're going to assume that we have to collect our own data, either through an observational study or through an experiment. And the questions that we answer could deal with a single population, all right? Or we could compare 2 or more populations, all right? And you'll see examples of that later. Now, if we have to collect samples from more than one population, then we have to do sampling from each of those populations, obviously. All right, now these definitions are important, so that's why I'm stressing to you. Every time I think something's important, I will stress it to you so that you can maybe make some notes so that you know, all right, this is something I have to pay attention to. The definition of an observational study, all right? A study in which the characteristics of a sample selected from one or more existing populations are observed. So an observational study would be where you would not be manipulating any variables like you would do with an experiment, all right? So what is the goal of an observational study? Well, you're taking some information from a sample or a subset of your population, and you want to generalize it to the larger population, and draw conclusions about the larger population for those variables. So that is the purpose of an observational study. Now, here's the issue. An observational study may not be able, and I'll stress this, I'll repeat myself a few times, but this way you'll remember it. An observational study will not necessarily give you cause and effect relationships. You won't necessarily, because you're not manipulating or controlling your variables, you're not going to be able to know for sure whether one variable is causing another one, right? Maybe you might be able to say they're correlated, which means they're related, but you probably won't be able to say that that one variable causes the other. Now, if a observational study is well designed, then, and well designed has much to do with the way you're collecting the data. The sample can be designed to produce, it could be designed so that you can assume that it's representative of the population. Now, I'm going to say assume because we won't know for sure that it's representative of the population because typically we don't know very much about the population. Okay, let's go to the next slide. An experiment. So experiment's a little different. This is where we have a response variable, something that we want to change in some way. And we may have one or more what are called explanatory variables that you may influence or manipulate. So it causes a change in the response variable. Okay. So you want to see if what you're manipulating causes that change in the response variable, and therefore you're interested in a cause and effect relationship. You want to see if the change in the explanatory variable causes a change in the response variable. Now, these explanatory variables are sometimes called factors. So if you see the word factor, you know it's the explanatory variable, that which you're manipulating. And the response variable, of course, is that variable that you want to see if there's a change to. All right. So what the usual goal? You want to see a cause and effect relationship. In a well-designed experiment, the composition of the groups, now what are the groups? Well, you're going to create typically two or more groups, which are called experimental groups, and you want to see, and you're going to compare them, and you want to see if changing these experimental conditions leads to a change in response variable. And one of the requirements is going to be that you will randomly assign people or things, whatever is in the experiment, people or things. You're randomly assigning treatments to those people or things, right? It has to be random assignment so that the groups that you're creating are about equal in terms of other possible factors that you're not studying but could influence the response variable. All right, so that's what an experiment is. Cause and effect is its goal, and the way to get to that would be through random assignment of treatments to the experimental units, which could be people or things. All right, and this is just repeating what I just said. So this is an important distinction between observational studies and experiments. Observational studies are not good for determining cause and effect relationships, and a well-designed experiment is. All right, so that very important. Always exam questions on that. All right, and probably not just for the exam number one, but also for your final exam. So I always tend to have questions about that. Now, these other factors or possible explanatory variables that could be influencing your response variable are sometimes called confounding variables. Confounding meaning that they may not be related to the groups of variables that are in the experiment and could be influencing the response variable. And it's in such a way that you would not be able to tell whether the resulting change in the response variable is due to the change in the explanatory variable or maybe to these so-called confounding variables. Sometimes you just can't tell. Now, I'll just give you kind of a silly example. Suppose you are a store owner, all right, and you're having trouble bringing in enough traffic people, that means people into your store. And so you decide to hire an interior decorator because you think maybe the store's not snazzy enough. And the interior decorator makes some recommendations, and you make those changes to your store to make it more appealing for people to come in. But suppose simultaneous to you making those changes to your store, a mall opens up nearby. Some mall opens up nearby. And suddenly, after the mall opens and you make the changes, more traffic is coming in to your store. More people are coming into your store. Well, it may not be due to the changes that you made to the store. It could be changes due to the fact that there's this mall that's come open nearby and have all these people walking around near the mall and happen to see your store and walk in. So the mall is your confounding variable, the opening of the mall, and the explanatory variable in your study is the changes, the interior decorating that you did inside the store to make it more appealing. And you may not be able to tell which of those variables caused the increase in traffic, which is your response variable, increase in traffic into your store. So that's kind of a silly example, but that's an example of sometimes why confounding variables can be hard to separate from your study. Now, an experiment, okay, controls for these confounding variables by having people randomly assigned to different treatment groups. And the theory behind it is that these treatment groups have about the same amount of confounding variables in them, and so they sort of cancel each other out. All right, that's the theory behind it. All right, so this is a definition of a confounding variable. Again, you need to know this. So if you see it in a test, you'll know immediately what it means. Now, of course, the tests that you have are going to be open book. So these definitions are in your textbook, but I would still take some time to learn them. You don't want to learn something during a test. And you may want to tag or write down the page number that's in your book to point to where these definitions are. All right. It's a very efficient way of studying, of having, of being prepared for your test. All right. Drawing conclusions from statistical studies. There's two types of conclusions that you can come to from in general. I mean, this is, of course, a beginning course, so they're talking in very general terms. One type of conclusion is the ability to take the results from your sample and generalize it to the larger population. All right, if you can't do that, then whatever results you get from your sample or from your study applies only to those people in your study, does not apply to the larger population. All right, so that's important, obviously. The other involves reaching a cause and effect conclusion, all right, about the effect of an explanatory variable on a response variable. Obviously, that type of conclusion can only occur during a well-designed experiment. Typically, we don't come to that type of conclusion in an observational study. And this last slide here is very useful. Again, I would pay attention to this because it gives you sort of an idea of what we just talked about. So along the left column here are different types of descriptions of studies. And along the right here are the two types of conclusions that we can make. In the second column, middle column here, can we generalize the conclusions from the sample to the population? And then we have yes or no. And on the right column, can we draw a cause and effect conclusion from that study? Well, obviously, the first two study descriptions say observational studies. So we know immediately the answer is going to be no to cause and effect. All right. So observational study, no to cause and effect. Now, there are some advanced, I have to tell you, there are some advanced statistical procedures that increase your chances of drawing cause and effect conclusions. All right. There are some procedures, more advanced procedures, but in general, it's harder to do that with an observational study. So for all intents and purposes for this course, since it's an introductory course, we're just going to say no to drawing cause and effect conclusions with an observational study. Now, let's look at the middle column for observational studies. We have a yes and a no here. The yes says, yes, you can generalize to the population. When? Well, when the observational study with the sample selected at random from the population of interest. Now, we're going to learn about that in a minute from the next section, section 2.2 on sampling. We'll understand why when we say random sampling. So the answer is yes, you can generalize to the population when you select your sample randomly from the population. However, if you don't randomly select from the population, if you have what are called convenience or voluntary response samples, which is a poorly designed sampling plan, then the answer would be no. And this idea of convenience or voluntary response sample we'll talk about a little bit in the next section. As far as experiments are concerned, all right, again, we're experimenting with groups formed by random assignment of individuals or objects to experimental conditions. So this random assignment is critical. What's it critical for? It's critical when we want to draw cause and effect conclusions. All right, without random assignment, you can't draw any cause and effect conclusions. All right, so there's one thing that you have to remember. With an experiment, you must have random assignment of treatments to individuals or objects to even have a chance at drawing a cause and effect conclusion. All right. So we're assuming that here. So we notice here that the answer is yes to the third column for both of those cases under random assignment for experiments. Look at the middle column, we see a no and a yes to generalizing it to the population. Now, even if you have a well-designed experiment, if the people who come into your study are volunteers or not randomly selected from the population, then we cannot generalize the results to the general population, which makes it kind of a shame, right? You have your cause and effect relationship, but if they're volunteers, we can't necessarily say that the results that we get apply to the population of interest. So in addition to randomly assigning people to or objects to our treatments, all right, we must also make sure that the people that we select for the study are randomly selected from the population. And we have to meet both those conditions to have yes, yes. Yes to generalize to the population, and yes, we can have cause and effect. So this is the best of both worlds, right? We can answer yes to both questions only in the case when the experiment, which randomly assigns treatments to individuals or objects, also has the experimental units or the people themselves randomly selected from the population. And the worst situation would be an experiment where we don't have random assignment and the people were not selected from the general population and randomly selected from the general population. And in that case, we would have no and no. All right, that's the worst case of a study right there. So this is a very good summary of this section 2.1 and one that you may want to look at again before you take your first test. All right, any questions about 2.1? I'm sort of like going pretty quickly here, but it's introductory. So I would highly recommend that you read, not just look at the slides, but read the chapter too, because whatever I cover in class may not necessarily cover everything that's in the section. So that's something you should realize, that the PowerPoints are good, but they're not sufficient to cover everything. All right, good. So let's move on to the next section, 2.2. Looks like there's some comment in the chat here. Let me see what the chat is saying. All right, so somebody else. All right, that's fine. So the Gennaro, that's fine what you wrote there. I understand. All right, so let's go back to the next slides, sampling. Now, in the In the syllabus, this was something we were supposed to cover on Wednesday, but I'm covering it today because there's a couple reasons why I'm doing it. Number one, this first section was so short. I wanted to cover this today. And secondly, I do think it would be helpful for you to have some background in experiments also. Although the rest of the course after chapter 2 is completed, although the rest of the course deals mostly with sampling, most of the examples are sampling. It's many of you, not many of you, some of you may actually be doing experiments in the future if you're actually going to be in some field that requires experiments. So it's good to have some background in experiments too. All right, so this is a section here which has quite a few slides, but we can get through it pretty quickly. Sampling. Now, sampling has to do with, it's a procedure of acquiring the individuals in your study in a random fashion. That's the whole idea of it. And the purpose of purpose of the studies to learn something about a population, to answer a particular question you have about the population, right? Something about it. Now, one of the things, this is very interesting, because when you talk to people in general, people maybe who have never taken a statistics course, and you talk about the idea of sampling, one of the first things that people will say is, I don't believe in it because samples are too small compared to the population, and there's no way it would represent the true population. And hopefully after today, and hopefully by the end of the course, you'll realize why that's a kind of a naive response, because the sampling procedure does work. And people, of course, will say something like, oh, well, look at the polls for the most recent presidential election, and they were wrong again. You know, the last two presidential elections, they were wrong. But I would argue that has less to do with the sampling procedure and more to do with the population from which you're choosing your sample in terms of the results from the poll. So we can talk about that at a later time. But the sampling procedure is an interesting one, because the question you may have is, well, if I do random sampling, and you can picture somebody randomly sampling by putting pieces of paper with numbers on them into some sort of box, and then you mix it up and you put your hand in there and choose randomly something or somebody from that box. That's what most people think of, when they think of random sampling. You're thinking, well, how do we know for sure that whatever we choose represents the population? And the answer is, we're not sure, because number one, we don't know the way that population's actually constituted. If we knew it, then we would not have to do sampling. We would know the answer to the population, what the population looks like in terms of what we're studying. But we typically don't know that. So we really don't know if the sample is a so-called perfect representative population. But what we're going to learn is that the procedure from which we do sampling gives us the best opportunity to have a representative sample. All right. So this is what they mean here. Our only assurance comes from the method used to select the sample, not from the sample itself. So again, that'll be made clear in a minute. Now, even if we do sampling, there's a possibility of what's called bias. Bias means that there's something about the sample that is skewed in a certain direction and makes it a bit unrepresentative of the population. All right. And there are different types of biases that can result, but it's something systematic. That's the whole idea. It's something systematic in the way that we're selecting our sample that results in some sample being not so representative of the population. Now, what are the types of biases that occur? Well, there are many types, but again, the three types that we're going to focus on here are selection bias, measurement or response bias, and another one called non-response bias. So we'll take each one of these separately in terms of a definition. Maybe I can give you an example of these. I think the selection bias one, they have an example in a future slide. So what is selection bias? It means a tendency for samples to differ from the population as a result of systematic exclusion of some part of the population. Now, this is an example of what I was talking about with polling, political polling. One of the problems sometimes is not the procedure that we're doing the polling with, it's that the population from which we're choosing is not really the population that we think we're choosing. So what in real life do pollsters and other people do sampling do? They create what's called, and this is a term that you might see in the textbook, they create what's called a sampling frame. Sampling frame, F-R-A-M-E. Now, what is a sampling frame? Well, for example, if we wanted to have a list of all the people in the US, well, believe it or not, there isn't such a list that exists. Now, there are countries in Europe, smaller countries, that do have lists of every person that's in that country. They do have such a list, but they don't have such a list in the United States. So people who are statisticians who do sampling for a living, they have to come up with some other method of finding people and or coming up with a list of people, and they use what are called sampling frames. So they have some sort of way of finding households, geographically or something like that. Maybe they sample households as opposed to people. But here's the point: the sampling frame, whatever they come up with, it may be not perfectly representative of the population. All right, it may exclude people that should be in the list, and it may include people who should not be in the list. All right, so the samples are being taken from the so-called sampling frame, and therefore the people being chosen may not, right off the bat, may not be representative of the population just because of the fact that there is a selection bias. We're leaving out or we're including, we're leaving out people that should be in the population, and we could be including people that should not be. All right, so that's something to consider. Another type of bias is called measurement or response bias. I think a good, now what does this mean? It means there's some systematic way that the measurement is giving wrong results. So suppose we were weighing people, all right, weighing people, and suppose the scale without any weight on it shows a +2 pounds on it, all right? So what does that mean? That means everybody who gets on the scale, the measurement of their weight is going to be 2 pounds heavier than they really are, automatically. So that there's a bias right there that's systematic, and it's because of the measuring instrument. There could also be what's called a response bias that has to do maybe with a questionnaire. Suppose one of the variables is an answer to a question on a questionnaire, and maybe the way that the question is worded will tend to make people answer in a particular way as opposed to another way, right? That can happen in questionnaires. So that means that there's a bias automatically towards one answer as opposed to another. So that's an example of response bias. All right, so measurement and response bias are considered to be very similar types of bias, so they're lumped together here.
What did you say was an example of measurement bias, Professor?
Would be like if you were, the variable was measuring weight of people, and suppose the scale that we're putting people on is without a weight on it, shows, instead of 0, shows +2. +10, whatever the amount is, then everybody's weight is going to be that much more, right? It'll be +2 pounds more than the weight should be. So the point of the matter is the measuring instrument could be producing a bias in the measurements that we're getting. And then the response bias, it would be something similar in terms of a questionnaire, where the question tends to lead people to a particular answer versus another answer. All right, does that answer your question?
Yeah, thank you.
Yeah, good. All right. And then the third type of bias is called non-response bias. Now, this happens typically with questionnaires, all right? Many, many years ago, before they had the internet, there was only a couple different ways that you could be contacted to participate with a questionnaire. One way would be in person, either in a mall, or maybe somebody would come to your house, or it could be mailed to you, or you could receive a telephone call, all right? Be mailed to you. Now, here's the thing. If it's mailed, right, you would think that many people would just throw it into the trash. And these questionnaires, when they randomly select, when the companies that do these questionnaires, when they randomly select people to be in the study, it really biases the study a bit when people aren't participating. They're not responding to the sample, to the study. So that's called non-response bias. And why is it a bias? Because the people who are not responding could have a different opinion maybe about a question as opposed to the people who do respond. So we'd be biasing the results in a certain direction. All right. So that's called non-response bias. So these types of biases can occur regardless of how we randomly select people, which we're going to talk about next. These biases could be built in to our study, even with a good way of collecting the data. So just be aware that these biases can exist. Now, here's another thing, because sometimes people have this opinion, which I don't understand why they would have this, but this opinion saying basically that if we increase the size of the sample, when we see size, we're referring to the number of people that are in the sample. For example, if we had 100 people originally in our sample, we wanted to increase it to 200 people, then the sample size would be originally 100, and then we would increase the sample size to 200 people. That's what we mean by size. Increasing the size of the sample, although possibly desirable for other reasons, which we'll find out later in a future lessons, it does not reduce these biases that we just talked about. All right. So even if the method of selecting the sample, well, even if we randomly select properly and we increase the size of the sample, if we don't reduce these biases in some way, or if the non-response rate remains high, these biases will still exist. All right. Increasing the size of the sample does not get rid of these biases because they're systematic. All right. So let's just take a look at an example here. I think that they're going to be talking more about one of the biases here. It says many surveys are conducted by telephone, and participants are often selected from phone directories that include only landline telephones. All right. For many years, it was thought that this was not a serious problem because most cell phone users also had landline phones, right? And therefore, they would still have a chance of being in the survey. But now, as you probably know, because many of you probably don't have landlines, because you have a cell phone doesn't mean you have a landline, right? Many more people are dropping their landlines, and they just have cell phones. So if surveys are just contacting people with landlines, then they're going to be missing quite a few people from the population. So this is an example of selection bias, where we're leaving out people who would typically be part of a survey, but are not being contacted because they just have cell phones, and these survey organizations are contacting just people with landlines. All right. So this is one reason. Another reason that we might find that our polling isn't quite right. All right. We're missing out on people who don't have landlines. All right. They give an example here. There was a study done that showed that for people under the age of 30 with only a cell phone, 28% were Republicans, compared to 36% of people who also had landlines, were landline users. So you could see that there's a distinct difference between these people who just had cell phones versus landline users in terms of the percentage of them who were Republicans. Obviously, that's going to have a big effect on polling. And if we just contact people with cell phones, we might be underestimating the number of Republicans voters, all right, in general. All right, so that was an example of selection bias, and I gave you examples of the other two. All right, now we're going to talk about random sampling, which again, I have to tell you that this is a topic that frequently comes up in test number 1 and also on the final exam, random sampling. So although I'm covering this at the beginning of the course, please make a note somewhere that you should go back to this when you do study for your final, because without going back to these topics from the beginning of the course, you may be missing very easy questions on your final exam, getting them wrong. And if you just went back and reviewed, you'd realize how easy the questions are. All right, so in the textbook, they talk about random selection as the vehicle through which you can generalize the results of your sample to the general population. All right, you can say something about the general population. Now, I can tell you up front that any type of random sampling, no matter the types that we're showing here, all have one thing in common, that everyone in the population, this is at least theoretically, everybody in the population has the same chance of being selected into the sample. All right, when you do random sampling, any type, period. All right. Now, let's talk about each one of these types. There's about 4 or 5 types that we're going to talk about in the next half an hour. All right. Type number 1 is called a simple random sample. Sometimes, and you may want to write this down, it's called SRS. All right, for simple random sample. All right. So if you see SRS, you know it means simple random sample. Now, it's a sample chosen using a method that ensures that each different possible sample of the desired size, and when we say size, we mean the number of people in the sample, has an equal chance of being the one chosen. Now, what does that mean? Suppose, now there's about 30, I think 36 people in this class. Suppose each one of you decides to randomly select 100 Rowan students to be in a sample, all right? And you have and you follow the procedure that they talk about here in a minute. We'll mention it. And so each of you randomly select 100 people. Number 1, do you think that all 36 of you would have exactly the same 100 people in your sample? Do you think that would happen?
No.
You could just unmute and yell out. Do you think that's even possible?
No.
No, of course not, right? Because random sampling would, if there is maybe 10,000 Rowan students and you're selecting 100 of them, good chance that all 36 of you will have different group of 36, different groups of 100 students in your sample. So what we want to do, however, with simple random sampling is say, all right, suppose we could list all the possible samples of size 100. All right, all the possible lists of the samples of size 100. We want to make sure that the sample that you choose has the same probability of being chosen from that list of all possible samples of size 100 of Rowan students. All right, so if let's say there is 10 billion, I'm just making this number up, but suppose there are 10 billion possible samples of size 100 from a population of 10,000 Rowan students. There's 10 billion of this. That means that the probability, if it's a simple random sample, the probability of choosing the sample that you get is 1 out of 10 billion, because there's 10 billion possible samples of size 100. Okay, does that sort of make sense? I hope it makes some sense to you. And that's what they mean here, is that the method that you use in simple random sample ensures that each possible sample of size 100 has an equal chance of being the one that you end up choosing. Okay, hopefully that makes some sense. Now, how do you do that? Well, suppose you had a list of all 10,000 Rowan students, and you assign a number to each one of those students. So there's somebody who's number 1, somebody's number 2, all the way up to somebody who's number 10,000. All right, so each student has a number associated with that person. And then what you do is you ask a computer typically to randomly select 100 numbers from 1 to 1,000, from 1 to 10,000. All right, so maybe the computer picks 9,220 for the first person. And then the second number the computer picks is 83. So the person who has the number 83 is selected. And that's how it does. It does it. It just randomly picks 100 numbers from 1 to 10,000. And those people, those students who are assigned those numbers are in the sample as opposed to people who aren't. Okay? So that's what we mean by simple random sampling. That's the more sophisticated way. You know, people, you know, if it was a middle school or a high school class, you would demonstrate this by what? You know, getting a box and having every student write their number on a piece of paper, throwing it into a box, having somebody come up and stir it around with their hand and pick, you know, maybe 5 of those pieces of paper out of the box. Right? And that's your random sample of 5 people. All right, same idea. All right, randomly selecting 5 people that way. All right, simple random sample. Any questions about that? And again, this ensures that each different sample of size, in the case I gave, 100, has an equal chance of being the one that you choose. All right. All right. All right, so here's an example. Suppose that we want a simple random sample of 10 employees chosen from all those who work at a large design firm. Maybe there are 200 people who live in this work for this design firm, and choosing 10 of them. For the sample to be a simple random sample, the method used to select the sample must ensure that each of the many different subsets of 10 employees, that is, all the different possible samples of size 10, are equally likely to be selected. All right. Now, they say here is if we have a sample taken from only full-time employees, that would not be a simple random sample of all employees. Now, it may happen, it is possible, that if most people in the firm are full-time and there are only a few part-time, it is possible that if you do a simple random sample, you may end up getting a sample which has only full-time employees, but that's just by accident. All right, it's not intentional. If we only sample from full-time employees, then that's not a simple random sample of all the employees. We have to include the part-time employees in there, or the temporary employees. They have to be included also. Okay. But it doesn't mean necessarily that the sample that we get will include the part-time employees. Now, there is a way of getting around that, which I will mention in a minute. Now, here's the deal. Although a simple random sample may by chance include only full-time employees, it must be selected in such a way that each possible sample, and therefore every employee, has the same chance of being selected. Each possible sample has the same chance of being selected. So here's the thing. What makes a sample a simple random sample? It's the selection process, not the nature of the sample itself, which determines whether the sample is a simple random sample. What process did we use to select the sample? You know, one that I mentioned, the one in terms of the computer, you know, numbering all the Rowan students from 1 to 10,000 and having the computer randomly select those numbers. That is a selection process. All right. We're not trying to think, all right, you know, we have so many ladies and so many men and so many people under 20 and some people over 20 at Rowan, so many undergraduates, so many graduates. Let's try to compose a sample that looks like. No, that's not the way it's done. It's done through randomness, through random selection. It's the process that determines the simple random sample, not trying to manipulate the sample to look like the population. Now, we use the small letter n to denote what's called the sample size, the number of people in the sample. Small n. And I just should let you know that the letter big N, the capital N, is used to denote the size of the population. They don't say it here, but that's typically what's used, all right? The small n is the number of people or things in the sample. Big N, or capital N, is the number of things, people or things in the population, if you happen to know the number. All right, so you'll see that small letter n used quite often in problems that will come up in the future. All right, so a simple random sample of size n, here's the definition: a sample that is selected from a population in a way that ensures that every different possible sample of size n has the same chance of being selected. Right? And here they're talking about the different methods that can be used to select a simple random. I mentioned a couple of them, right? And you know, I think they're the ones that they mentioned here. You know, writing numbers on pieces of paper and then selecting n of these pieces of paper one by one out of the box or whatever you're using. Obviously, there's some drawbacks to that. Now, here's the sampling frame that I was referring to earlier. All right, so please, this is the definition that I do test on this occasionally. So you have to understand that you may not have a list of the entire population, and you create a list called a sampling frame, which approximate what you think the population is. And again, it may not be an approximation, may include people who shouldn't be in there, may exclude people that should be in there. All right. We will identify everybody on the list or the sampling frame with a number, and then a table or a random number generated with a calculator or computers used to select those numbers one by one. And then you have your sample, right? Okay. Now, there's two different ways of sampling in general, right? And this is very important. So this is, again, very possible definition that could be tested, right? One is called sampling with replacement, and the other is called sampling without replacement. So I think the best way of understanding both of these is, suppose, and I usually describe this more when we do probability. So this concept will come again later with probability. But suppose we have a big box full of different colored balls that people, maybe beach balls or something, and they're different colors. All right, so we have white and yellow and brown, maybe, whatever. And suppose we select one of the balls at random. We look at it, we record what color it is. Sampling with replacement would then say, all right, we're going to put that ball back into the box and then mix it up and select another ball from the box. Well, it's possible, isn't it, that we may select that same ball again when we do that. And that's called sampling with replacement. So once we sample something, we put it back into the population, and then it becomes possible that it could be selected again at a later stage. Now, sampling without replacement means that we do not put that ball back into the box. All right. Now, why is that important? Well, if we want to keep the probability the same of each time we select from a population, we want to keep the probability of being selected the same, then if we sample without replacement, typically that probability changes. For example, if we had, let's say, 20 balls in the box, and maybe 5 of them are white and 15 of them are brown. All right. So if now we know the probability of selecting, if there's only 5 white balls out of 20, right? The probability of selecting a white ball would be 5 out of 20, right? Or 1 out of 4. And we'll talk more about that later. However, now, if we put the white, let's say we select a white ball and then we put it back into the box, then the probability remains the same, that it's 5/20 or 1/4 of selecting the white ball, and it would obviously be 3/4 for selecting the brown ball. However, if we select a white ball and keep it out, that means we sample without replacement, then for the second to select a white ball again, now there's only 4 white balls left, right? 4 as opposed to 5. So the probability of, and there's only 19 balls in the box. So the probability of now selecting a white ball is, for the second time, would be 4 out of 19. So the probability has changed. So that's the big thing. Sampling with replacement keeps the probabilities the same. Sampling without replacement changes the probabilities, all right? So obviously, sampling without replacement is not a great idea for sampling, right? Because we need to keep probabilities the same. So how do we get around it? Well, and here's the definition of sampling with replacement that I mentioned a minute ago. Here's the deal. It says, although these two forms of sampling are different, when the sample size, n, the number of people in your sample, is small relative to the population size, that would be uppercase N, big N. If the sample size is small relative to the population size, as often is the case, there's little practical difference between them. Why? Because if you have, let's say the population is 1 million, and your sample size is 100. Well, 100 is much smaller than 1 million. Okay, much smaller than 1 million. So when you when you do sampling without replacement, the probability doesn't change very much. It changes very little. And so we can assume that the two are practically, the two methods, sampling with replacement, sampling without replacement, are about the same, right? So in practice, it says here, when the sample size, small n, is less than 10% of the population size, big N, then we can assume that it's okay to sample without replacement because the probability doesn't change very much when we take somebody out. And why is this important? Is because when we do sampling, we typically, let's say we take somebody out of the population and we give them a survey question or survey questions, and then they complete the questionnaire. We're not going to tell the person, okay, we're going to put you back into the pool of people, and we may select you again and may ask you the same questions again. They're going to look at you like you're crazy, right? So that's not something that we do in sampling. We're going to do sampling without replacement. Once we sampled somebody, they're done. They're not going to be put back into the pool of people. They'll never be sampled again. So we want to make sure that the sample size is small relative to the population size, and that means the probability of being selected doesn't change very much when a person is selected in the sample. Any questions about that? Because that's kind of an important part of this idea of sampling. Okay, so how are we doing with time? Yeah, I think we have enough time to finish. I think we could finish the 21 slides that are left. All right. Here's an example here, which you can look through, by the way. I'm not going to spend a whole lot of time on this, but this is an example of simple random sampling. Is an example where it says breaking strength is an important characteristic of glass soda bottles. Suppose we want to measure the breaking strength of each bottle in a random sample of size n is equal to 3. So we're just selecting 3 bottles at random. And what are we going to select it from? 4 crates containing a total of 100 bottles. So our population is 100 bottles from these 4 crates. Each crate has 5 rows of 5 bottles each. So there's 25 bottles per crate, and there's 4 crates, so that makes our 100 bottle population. And we're just selecting randomly 3 bottles from these 100 bottles. And that's 3%. That's well below the 10% requirement for random sampling. And here's just an example of some of these crates that are filled. And what we do is we assign numbers to each of these bottles in these 100 bottles in these crates. And then we use some sort of process through a computer to randomly select the bottles. And then by just selecting the numbers, and each of these bottles has their own number. So we just randomly select numbers, 3 numbers, and then whatever numbers they are, we find the bottles in the crate and pull those 3 bottles out. And then we do our little test of the breaking strength of those bottles. All right, and again, use some sort of computer or calculator package that allows us to generate those 3 random numbers. And again, we asked the calculator or computer to select 3 numbers from 1 to 100, and those bottles will be the ones selected. All right, so now here's the important thing. Does random sampling guarantee that the sample would be representative of the population? No, but here's a very key part right here. We are able to assess the risk of an unrepresentative sample. Now, what does risk mean? It's another name for probability. We can actually assign probabilities, right? And therefore, we can determine what's the probability of getting an unrepresentative sample when we do select the sample, instead of just guessing at it. All right, and that is the strength of random sampling. It allows us to assign probabilities to the chance that we would end up with an unrepresentative sample. So we can quantify this risk, and therefore we can have confidence of making conclusions about the big population from this smaller sample. All right, this idea of quantifying the risk, quantifying the probability that's the only way we can do that is if we do random sampling, because then we can assign those probabilities. Okay, and this is something was noted, I think, in the previous section about the idea that if we increase that the size of the sample, if it's small relative to the population, the sample can reflect the population, right? And again, it's a common misconception that it can't, right? And now we know it can. It can because of the idea that random sampling generates probabilities, and we can actually quantify the probability of an unrepresentative sample. So here's an example. Population's 5,000 applicants to a state university, and suppose we're interested in the math SAT scores for this population. All right, and we're going to learn more about dot plots in the next section, next week. It's one of the graphs that we can use, but this dot plot here represents a distribution of these 500 scores, right? I think it was, no, 5,000 scores. So there are actually 5,000 dots in this dot plot here. As you can see, most of them are around 500. You know, most of the height here is the number of people. We've got those scores. So you can see most of the scores are somewhere between 400 and 600 for the math SATs. Suppose we took samples of different sizes and we wanted to see, does the distribution kind of come close to the spread of data that we see in the population? And as we could see, a sample size of 50 from the 5,000, here's the distribution, doesn't do a bad job of looking at the spread of scores. Most of the scores are going to be between 400 and 600, right? A little better distribution when we have a sample of 100. It gets better, obviously, as the sample size gets bigger, but even for a very small sample size of 50, it's not a bad representative of the population distribution, right? It's still the scores are still typically between, most of them are typically between 400 and 600. And that's true for any of these samples that are shown here. All right, so each of the samples tend to reflect distribution of scores in the population. All right, so we could have a sample of size 50, and it would work pretty well. It would give a pretty good estimate for example, if we wanted to know the average score the sample size 50 would give us pretty close estimate of the average for the whole population. All right. All right, so it does a pretty reasonable job. The only way it would not do a reasonable job if the sample size was really, really small. All right, if we only had 5 people in the sample out of 5,000, yeah, we probably wouldn't have a very representative sample. So there is a minimum sample size that we need, but it doesn't mean that if we have a population of 5,000, that we need 2,000 or 3,000 in the sample. We could have 50 people in the sample, and it would do a reasonable job. All right, so the selection process through random selection allows us to be confident that the resulting sample adequately reflects the population, even if the sample only has a small fraction of the population. All right, and that's important. Now, let's look at some of the other methods. Again, this is sometimes tested. I would say, well, not sometimes, all the time tested in the final exam, in my portion of final exam, and certainly in the first test that you'll get. So it's good to know the difference. Now, simple random sampling occurs from the entire population. We're selecting people randomly from the entire population. Stratified sampling is a little bit different. Stratified sample says we can take our population and we can break it up into groups, all right, subgroups, subpopulations, all right. And each of these populations, subpopulations, we take a simple random sample from each one independently. And we do so that the sum of all the samples of the subpopulations add up to the number of people we want in the overall sample. So here's an example here. Suppose we wanted to estimate the average cost of malpractice insurance, and a researcher finds that it's more convenient to view the population of all doctors practicing in a city being made up of 4 different types of doctors. We have surgeons, we have internists, we have family practitioners, we have obstetricians, and then we have all the other specialties lumped into group 4. All right, what are we going to do in this case here? We're going to take a simple random sample from each of those groups. So in group number 1, surgeons, we're going to take a simple random sample of, let's say we wanted, just to be consistent here, let's say we wanted 100 doctors altogether in our sample. And suppose we want to take a simple random sample of 25 surgeons, 25 internists, 25 obstetricians, and 25 in group 4. That would make up 100, right? So we do a simple random sample of just the surgeons. We do a simple random sample of just the internists and family practitioners. We do a simple random sample of 25 of obstetricians. A simple random sample of 25 of this group 4. So we do a simple random sample of 25 from each of these 4 groups, and that adds up to 100. Now, we don't have to do simple random sample of 25 from each group. We could have different numbers, but the whole idea is to add up to 100. Now, what's the advantage of doing this? Not only do we have information about all the doctors, but we also have information about each of these groups. We could have, for example, we can have the mean cost of malpractice insurance for all doctors, but we could also have separate means for the surgeons, for the internists, and for family practitioners, for the obstetricians, and for the group number 4. So that's a big advantage of doing that. Right? So each of these subgroups are called strata, right, or strata, depending on how you say it. And each individual subgroup is also called a stratum. I guess I'll say stratum. So in one group, one of them is called stratum, and if you have more than one, you call them stratum. The stratified sampling selects a separate simple random sample from each stratum, and each stratum is just a group, and each group is non-overlapping. That means a doctor couldn't be in 2 groups. That doctor's only in one of those groups, and it includes all doctors. All right, so you got the whole population, and you're selecting simple random samples from the 4 groups. Right. So what's the real advantage of doing this? You have more accurate information. They call it inferences about a population than does simple random sampling, because you're going to have group information also, these subgroups. if the subgroups are homogeneous, now what does homogeneous means? They're alike, they're similar to each other. So if, you know, surgeons are all going to be surgeons, and you have your internists are all going to be internists. So you want these strata to be homogeneous, means everybody in their groups are similar. All right. Now, this is where people get confused sometimes between stratified sampling and this type of sampling called cluster sampling. So what is cluster sampling? We do the same thing. We divide the population into non-overlapping subgroups. All right. But this time we're going to call them clusters instead of strata. And what do we do in this case? What we're going to do is we're going to select the clusters at random, not people. We're going to randomly select clusters. So suppose there's 20 different subgroups in a population, and we want to select maybe 3 of them. So we do simple random sampling of clusters, not the people within the clusters. And then once we have those 3 clusters, we select everyone in each of those clusters to be in the sample. All right. So that's called cluster sampling. Now, when do we do that? We do that when these groups are kind of mini populations. That means they are heterogeneous. They are different within the cluster, different people, different types of people in the cluster, sort of mimicking somewhat what the population would look like. All right. So that's called cluster sampling. And then we have another type of sampling called systematic sampling. Systematic sampling occurs when we have a list and we want to go through the list systematically. An assembly line in a factory is an example of this. All right, so suppose we want to have a sample of so many people. What we do is we pick a certain number, K, could be 50, could be 200, and then we let the computer pick a number between 1 and K. So if, let's say K is 50, the computer would then pick some number between 1 and 50. Suppose it's 32. And that means the 32nd person on the list, or the 32nd box off the assembly line, is the first one selected. And then, since K is 50, then every kth individual would be selected after that. So for example, if the first person or first box off the assembly line is number 32 and K is 50, that means the 50th box after 32 would be the next one selected. So 50 plus 32 is 82. So the 82nd box is selected. And then the 50th box after that is selected, which is the 132nd box, like that. And that's called a 1 in K systematic sample, right? So this works in terms of assembly line, in terms of you have, let's say, a list of people and you want to select people in going from first down to the last person. This is one way of doing it. This doesn't work very well if you have repeating patterns within the list, so it doesn't work very well for that. They do give an example here. For example, at a university, suppose you want to select, let's say, so you have a sample faculty members might be selected from a faculty phone directory. One of the first 20 faculty members would be randomly selected. Okay, so K is 20, and then the 20th person after that would be selected. So for example, if you randomly select a number from 1 to 20, and suppose it's 3, then the third person on the list, you just run the number, your finger down to the third person. That would be the first person selected, and then the 20th person after that would be selected. So 20 plus 3 is 23, and then the 23rd faculty member selected, and then the 20 after that would be 43, like that. All right. So that's how you would acquire your sample, and it describes here mathematically how it works in the slide. All right. And then finally, the last method, we have 1 minute left, is convenience sampling. This is not random sampling. This means convenience, such as voluntary sampling, or let's say you're at a mall and you see a couple buses pull up and you say, all right, I need 100 people, and it seems like there's 100 people in those two buses. I'm just going to interview those two people, two buses, and I'm done. That's called convenience sampling. It's not random, doesn't work well, and can cause all sorts of biases, and it's bad. And one thing about convenience sampling, you cannot generalize from the sample to the population. All right, so just know that it's not good. And a lot of internet type sampling is convenience sampling, and it doesn't work very well. And that's it. All right, so stop sharing. I think time worked out pretty well. Any questions? So I would recommend very strongly that you read these two sections before the next class. Maybe you have some questions before the next, at the next class. I will cover experimental methods and the terminology regarding experiments next time. That's sections 3 and 4. Section 5 in the book will not be covered. All right. No questions, so I will stop the recording.